Hello there. Welcome to section 1.4, the matrix equation AX equals B. In this section, we are going to rephrase some of the concepts from the previous section in new ways. So it's going to be more of the same thing, but new terminology. In section 1.3, we talked about linear combinations in the vector equation like this. And we also saw that this equation would lead to a definition, which is this. So we talked about how AX can be written as this matrix times this matrix, which in turn results in this linear combination. Now, this definition is only true, or AX is only defined if the number of columns of A equals the number of rows in X. So basically, the way I like to think about it is if this is let's say a 1x4 matrix, then this one needs to be a 4x1 matrix. And if that's the case, these are the same, and so we will result in a 1x1 matrix. Okay, so just food for thought. So let's look at some examples here. Here, remember when we are looking for the dimensions, it is always rows by columns. So in this case here, we have 2 rows and 3 columns. So this is a 2x3 matrix. And this one here has 3 rows and 1 column. So this is a 3x1 matrix. The number of columns in the first matrix is the same as the number of rows in the second matrix. So our resulting matrix will be a 2x1 matrix. So we can find the following. What I'll do is I will basically split this up into several matrices in order to write a linear combination. So I'm going to take this piece here and multiply it by the first entry. So I'll have 7 times the matrix 2, 1. I'm going to add that times this times the second entry, or 2 times the matrix 3, 0, plus this times the third entry, 1 times the matrix -4, 5. Okay, well, applying the information we learned in the previous section, these are all scalars, so I'm just going to multiply them. So this becomes 14, 7 plus 6, 0 plus -4, 5, and then adding the corresponding entries, I end up with the matrix 16, 12. Excellent. Go ahead and pause this and see if you can do the next one. Here I have 3 rows by 2 columns and 2 rows by 1 column. Since these are the same, my resulting matrix should be a 3x1 matrix. So when I do this, I'm going to take this column times this entry, plus this column times this entry. Apply the scalars to get -10, 4, -6, 28, 7, and 0, and then add the corresponding entries. to get 18, 11, negative 6. Okay, so that is basically applying the definition AX equals B. Now, as mentioned at the beginning of this video, we're going to see a lot of different notation, but really it is all the same thing. And that is what this theorem here is telling us. This tells us that a system of linear equations can be viewed in 3 different ways. It can be viewed as a matrix equation, a vector equation, or as a linear equation with an augmented matrix. All of these are solved in the same way, by row reducing the augmented matrix. Okay, so all of these things are the exact same thing. You'll see that this matrix equation has the same solution as this vector equation, which has the same solution as this augmented matrix. So when you are working on these problems, you'll just want to be cautious of the way the directions are stated because it's basically going to be asking you the same thing. So here, this leads us to the next theorem. It's basically saying that an m by n matrix, if A is an m by n matrix, this is a lazy mathematician way of saying the following are equivalent. And that's basically some of the things that we've talked about previously, that this equation does have a solution, that B is a linear combination, that the columns do span, and that there is a pivot position in every row. Let's go ahead and see what we can come up with here. Okay, here is our first example. And all this says is compute AX, where A is this and X is this. So we are just going to take some baby steps, all right? So AX is equal to, well, matrix A is stated for us there. Make sure when you write this out that you have written each entry correctly. So this is matrix A, and we know matrix X is this one here. So X1, X2, X3. Well, as shown in our previous examples, what we want to do is we want to take this column times this entry and rewrite that. So X1 times 3, negative 2, 7. Then we're going to add that to this column in this entry. So that should be a negative 1. And then finally we are going to add that to this column times this entry. All right, excellent. So now we are just going to multiply by the scalars. So multiply these. So we end up with the following matrices. 3x1, negative 2 times x1, 7x1, plus 2 times x2, 4 times x2, negative 1 times x2, plus 3x3, negative 2x3, 8x3. All right, and then we will put them all together by adding the corresponding entries to get the following. 3x1 plus 2x2 plus 3x3 for our first row. Our second row is negative 2x1 plus 4x2 minus 2x3. And finally, our third row is 7x1 minus x2 plus 8x3. And this concludes the example. There's nothing more we can do. So here we have AX is equal to this matrix here. There is another way in which we can solve this, and it's basically putting together a few steps from the previous examples. So basically, if you read through this, AX, so that multiplication, what we just came up with, is defined as that specific entry of the sum of the products of the corresponding entries from row I in the vector X. So there are a couple ways we can do this. We can do this as we did previously. So we could take this times this entry, add it to this times this entry, so on and so forth. And this is the exact same problem from example 1, okay? So that's what we did. But a new method, this row vector rule, says that what we can do is basically take this row and multiply it by everything in this column. And this is kind of what you're taught in, say, a lower level algebra class. So what we would do is we would take this first entry times the first entry plus this times this plus this times this. And if you calculate this, you will get 16. Similarly, using the next row, same column, if you take the first entry times the first entry, plus the second entry times the second entry, plus the third entry times the third entry, you will end up getting 12. This matrix is the exact same thing that we got in example 1, just a different method. So what you'll do is you will take the first row, multiply it by everything in this column. Once you've done that, then you move to the next row, multiply it by everything in this column. Once you've done that, you move to the last row, multiply it to everything in that column. See if you can do that by pausing this video, and then I'll show you how. So we're going to take this first row, multiply it by everything in this column. So negative 5 times 2 plus 4 times 7. Then we're going to take the next row, multiply it by everything in this column. 2 times 2 plus 1 times 7. And then finally, the last row, same column. Negative 3 times 2 plus 0 times 7. Now looking at this, hopefully you notice some patterns. All of these are multiplied by the first entry. All of these are multiplied by the second entry. Same thing here. But when you multiply this all out, you will end up with the same thing from example 1. So this is just showing that there are a couple different methods to solving these. There's a little something called the identity matrix, and the identity matrix is a very special matrix where at the diagonal there are all ones and every other entry is a 0. Basically, what that means is if you take this matrix and multiply it by any other matrix, it's basically like multiplying by 1. You will end up with whatever that other matrix is. So if you look at this example I've provided you with here, this is the identity matrix, and I'm multiplying by this other matrix, so we should see that this result ends up with this matrix. But of course, you can apply the rules that I just taught you to verify. So what I would do is take this row times this column. So 1 times R plus 0 times S plus 0 times T. Then take this row times this column. 0 times R plus 1 times S plus 0 times T. And then the last row, same column. 0 times R plus 0 times S plus 1 times T. And when you simplify all of it, you end up with this matrix here. So the identity matrix is something pretty darn special. It's basically like multiplying by 1. The last thing I want to show you here is Theorem 5. Basically, it is summarizing everything that we've talked about. If we want, we can rewrite this as follows, and same type of thing with the scalar. The scalar can either be multiplied by the vector, or we can take it on the outside. Either way is fine. If you are dying for some mathematical pleasure, you are welcome to refer to the proof in the text. Enjoy!